Hello everyone, welcome to another class of fundamentals of particle and fluid solid processing. Today we will look into the other aspect of fluid particle mechanics, that is the motion of particle in fluid. We have cleared our concepts, or we have revisited our concept on the boundary layer and the drag force. Now we will see its utility for this particular subject and its relevant places. So, the motion of solid particles in a fluid, there the drag force comes into act. Now, the drag force in creeping motion or the creeping flow, we know now what is creeping motion between a rigid sphere of a diameter x and the fluid of infinite extent. That means, let us say there is no effect of boundary wall. Okay. Say there is 1 meter column of some water conservation size of the pot, and a sand particle of 2 millimeter is falling there. So, basically the size comparison between the object that is falling on this pool of liquid where it is content. So, that comparison is very low. Okay. So, in that case we can say that there is no effect of boundary wall or the fluid is of infinite extent. So, in such case the pressure drag force is pi x mu u. Okay. The u is the velocity that is falling. The shear stress drag, this is the thing that we have seen, the 2 pi x mu u, this is the shear stress drag, and so the total drag force that resists the motion of this object while falling, okay, in a stationary liquid or stationary fluid is basically F d, which is the shear drag force plus this pressure drag force, and is 3 pi x mu u, which is basically the Stokes law that we have seen, or we in fact this one we have derived in one of the examples when we have solved this, where u is the relative velocity between the object and the fluid media. So, this Stokes law gives the drag force on a single particle, okay, with a relative velocity u of diameter x. Okay. So, why such thing is important? Because we have discussed it that when we try to separate, let us say, multiple particles, okay, by its size, okay, we will see that it settles different particles of different sizes settles at a different rate. Okay. Now, based on that we can have size separation of several particles. So, for that we have to understand that how much drag was acting on those particles. Now, you can see that the drag force is proportional to the size of the object, okay, where x is that diameter. In case of a spherical particle, x is the diameter, okay, or in other irregular shape it is the equivalent diameter. Okay. Mu is the viscosity of the fluid, u, as I said, it is the relative velocity. Now, this Stokes law, this drag force calculation for a single particle works exactly when the flow is creeping flow. That means, way below the value Reynolds particle Reynolds number 1, and specifically it is exactly the same value when the Reynolds particle Reynolds number is beyond 0.1 or so, and it works reasonably well within the 10% error when we apply this in the region of this Reynolds number lesser than 1 and higher than 0.1, where again the particle Reynolds number are defined as this expression where x is the diameter of the particle, okay, or the object, u is the relative velocity, rho f is the fluid density, and mu is the viscosity of the fluid in which the particle is settling. Okay. Now, we can calculate also this CD, okay, or the drag coefficient, where we have seen this R, which is basically the force per unit projected area, or Fd by A, that we mentioned earlier. Okay. And for sphere, this F, the drag force, or the R prime here, is basically the overall drag force Fd divided by its surface area. Okay. So, in Stokes' law, in terms of drag coefficient, this CD is basically 24 by Rep. So, Stokes' law that gives us the drag value Fd is this one, okay. And if we try to represent this instead of Fd with this CD value, okay, after replacing this Fd with this expression here, okay, and the CD, then here we get the CD value as 24 by Rep. Okay. Now, this right hand side schematic, what it shows, that this CD versus Rep plot. Okay. In this case, it is a log-log plot. So, x axis is in the logarithmic Rep, okay, and this y axis is the log CD. So, here we can see that this CD versus Rep for a range of Reynolds number around 0.3, this relation works. So, we typically say that this Stokes' law is valid typically till a particle Reynolds number of less than equals to 0.3. Okay. So, you can ask that what is this value that I have mentioned here? It is the particle Reynolds number. If it is below 0.1, then definitely this solution gives the exact value. In this range, it gives the exact value of this drag force. As it increases, it holds true, but it gives a certain error, which is well within the acceptable limit, because till the value 1, somewhere here the error is only 9 to 10%. Okay. So, typically those if you do not consider that 9% is the acceptable accuracy limit, it holds true well till 0.3. Okay. So, Stokes' law is applicable till the particle Reynolds number of 0.3. Okay. If you apply it beyond till the Reynolds number value 1, you can have till reasonable accuracy value, okay, but beyond that it is not acceptable. So, the point is that as at the higher relative velocity, the inertia of the fluid dominates, okay, because the Reynolds number has increased. So, the inertia of the fluid is now dominating, okay, and then there is no analytical solution of this Navier-Stokes equations under these conditions, because as that happens at relatively higher velocity, there is acceleration. Okay. So, typically what happens, the drag curves have been developed for such scenarios. Okay. The experiments provided such relationship between the drag coefficient and the particle Reynolds number, which is shown here. So, here the y axis log CD and this is the log Rep. So, we can see that this whole plot can be divided broadly into 4 portion or the 4 region. One is where the Stokes' law is valid. One is the position where the Newton's law is valid. Okay, that means in this Newton's law you can see the drag is basically independent of the Reynolds number, it is a constant value. Okay. In between these there is some intermediate portion, okay. And outside this Reynolds law region there is the boundary layer separation region. Okay. So, if you remember this schematic, then it would be easier for you to understand that there is initially for the low Reynolds number or the creeping flow region, there is this relation CD is equals to 24 by REP is valid, is there. Then there is intermediate portion, after that there is a flat portion where the CD is independent of RE, and then there is boundary layer separation. So, in these two region the calculation of CD is bit complicated. Okay. We see that for this Stokes region, when this REP is less than 0.3, we have the CD value 24 by REP. In the Newton's region, we have numerically equals to 0.44 the CD value, which is pretty much constant, and this range of the REP that we say is in the Newton's region is this kind of a value. Now, we can see that once it crosses such numbers 10 to the power 5, 10 to the power 5 into 10 to the power 5, then that critical Reynolds number has been achieved and it becomes turbulent, and all these things of flow separations and all these things happens. Okay. Boundary layer separation happens. So, in this intermediate region there are several correlations that are available to calculate this CD, and one of such is given here, that is proposed by Schiller and Naumann. They are the scientists, they came up with a research paper where they proposed that this relation holds true with an accuracy of around 7% for a single sphere. Okay. For the entire range, if some this Hyder and Levenspiel also tried to contribute or to come up with the overall relation for this entire range, and that has a kind of complex formation or the form these relations. These relations you need not remember. Okay. This is to show that how this complicated, these are basically the empirical relations. After doing several experiments, they come up with such fitting parameters to fit the CD versus REP relation. Okay. So, I hope it is now clear that in this 4 region, Stokes region, intermediate, Newton's region and the boundary layer separation, we have a clear idea about this region and Stokes law and the Newton's law region, what is the CD value and what are the types of this overall entire region and the intermediate region, how the relations between the CD and REP. Okay. Now, when there is a particle that is falling from rest in a fluid, okay, typically this is the force balance. Okay, that is the gravitational force minus buoyancy force minus drag force is the acceleration force. So, initially it experiences high acceleration as the shear stress drag is small, okay, or as a lower value, because this shear stress drag increases with the relative velocity. Now, as the particle accelerates, okay, so the scenario is that there is a pool of liquid, you just drop a particle in that pool of liquid. So, initially that particle will accelerate, okay, will attain a high velocity and then that velocity is maintained. Okay. So, there is a force balance that is attained when the acceleration is 0, okay, and at that time it attains a maximum or the terminal velocity, we call it as a single particle terminal velocity, at which it will now settle. So, for spherical particle, then this force balance this gravity minus buoyancy minus drag is equals to 0 when there is no acceleration, this balance will give us the terminal velocity value. Okay. So, here a spherical particle having diameter x is, this is the gravitational force, this is the buoyancy force, where rho f is the fluid density where it is falling, rho p is the particle density, okay, and this is the drag force on the projected area of the sphere. Okay. So, this is how we are applying our previous knowledge in this calculation. Okay. And in fact, such balance we have seen earlier in our solution of the drag force problems. Okay. And here again the CD we have seen as this expression, that is the force per unit area divided by the half rho f u square. Okay. If we now replace this r prime in this expression with the CD, okay, that comes from this expression. Okay. We have this whole equation, fine, and now we term this u as ut, because this is the single particle terminal velocity when the acceleration is 0, and this is the maximum velocity in with which the particle will settle. Okay. So, if we now rearrange this expression to find out the CD, it gives this expression. What is the CD on this single particle? Okay. So, this is the relative density, density of the particle minus density of the fluid divided by the density of the fluid, 4/3 rho g multiplied by the diameter and ut square or the terminal velocity square. So, now if we know the CD, we can calculate that what is the terminal velocity. Okay. Now, to know the CD, again we have to understand what, in which regime, which regime or region we are talking about. That means, is it in Stokes region or in Newton's law region or intermediate region. Okay. So, for Stokes law region, we know the CD value. If we equate that in this expression, we can have ut values, which is given here in a simplified manner. So, if you replace this CD value by 24 by REP, you expand that REP expression with x, rho, mu and the nu, which is the kinematic viscosity. Okay. You find that ut is deduced as x square relative density multiplied by the g divided by 18 mu. Okay. So, this is the terminal velocity in the Stokes region, which means when particle Reynolds number is less than equals to 0.3. In the Newton's law region, from the Newton's law region, as if you remember that this is 500 to 2 into 10 to the power 5, such kind of value, the CD value was 0.44. In that case, if you replace here as 0.44 and calculate ut, you find ut as 1.74 multiplied by this parameter. Now, the point you should note here is that in the Stokes law region, the terminal velocity or the velocity at which it will fall is proportionate to the particle diameter square, the square of the particle diameter or the size, and here in the Newton's law region it is root over of that particle size. Okay. Now, which means if you can create a Stokes law region, bigger particles will fall in a very fast, relatively very faster than the smaller particle. Okay. As the particles will be bigger, it will fall faster and faster, because it changes with the x square. In the intermediate region, as such there is no correlation, but again it depends on these parameters, that is somehow people have come up or the researchers have come up with this kind of a parameter that it proportionately it is proportional to the x to the power 1.1 or the diameter to the power 1.1, relative density to the power 0.7, this kind of a number, okay, which means you can understand it is difficult, and as such there is no clear cut correlations or something that is available to do that. So, there are situations that you have to calculate the terminal velocity for a known particle or the known size particle, or the other way around, that for a given terminal velocity you have to calculate the particle diameter. So, how do we do that? Because in both the cases, in these cases the flow region is not known. Okay. So, what happens if it falls in one of the region? Would you do it arbitrarily, or there is some method? The one of the method is that to calculate this curve, this term, the CD multiplied by the REP square and CD by REP. Now, these parameters has some unique benefit. For example, if there is known particle size, and you have to calculate the terminal velocity, or you have to find out what is the terminal velocity at which it will settle. The thing is that you must remember that schematic of log CD versus log REP, log CD in the y axis, log REP in the x axis. Okay. And if you calculate this parameter CD multiplied by REP square, okay, the expression will be this one. Okay. And you can see this parameter is independent of the terminal velocity which you are calculating. Okay. Your task was to calculate the terminal velocity of a known size particle. That means, in this expression everything is there that would be given to you. X is known, other fluid and the physical properties are typically given. So, you can easily find out this CD versus CD multiplied by REP square. Now, if you plot this parameter CD versus REP square in a log graph, what it would produce? It would produce a straight line of slope -2, because CD multiplied by REP square is basically constant for this problem, because if you are given particle size is there, all other physical properties are same, this parameter is basically constant. Okay. On a logarithmic coordinate or on that drag curve, if you remember that log CD versus log REP, it produces a straight line of slope -2 and it intersects that drag curve somewhere. That point, that intersection, that you can find out that that is your REP. Okay. So, because remember, when you try to calculate REP, you basically needed that terminal velocity, isn't it? It is the dV rho by mu. So, let us say the d diameter is known, V, that V is what you are calculating. Okay. But if you get now the Reynolds number, you can now calculate what is your V. Okay. So, how it looks like is that this is the log CD versus log REP graph. This CD REP square will create such a line on this graph, standard drag curve. Okay. So, this intersection is what you can read that this is your REP then. Okay. Now, if REP is known, then you can calculate the UT, because all other parameters are known. Okay. Similarly, if the particle size is what you have to calculate and the terminal velocity is given, then also you cannot calculate Reynolds number, because Reynolds number is again x u mu rho by mu. Okay. So, but in that case if you find out this parameter CD by REP, you will see that this parameter is again independent of the particle size. There is no x in this term, and again this parameter on this curve will put a straight line of slope positive 1. You find out its intersection with the standard drag curve, you find out the REP, you find out what is your x or the diameter of the particle. Okay. So, I hope such, if you were given either of this problem, you should be able to calculate this either the diameter or the terminal velocity for a given problem, even though your flow regime is not known, provided such CD versus REP graph is supplied to you, or CD versus REP table is supplied. Instead of this graph, there can be a possibility that you are supplied with the CD versus REP data sheet. Okay. There also you can do this, we can find out what would be the intersection point. Okay. So, what we have covered today is the motion of a single particle in a stagnant or the stationary pool of liquid where there is no effect of boundary. We have seen the validity of the Stokes law, we have seen what is Newton's law region, we have seen what is the CD versus RE curve or the entire range, how it looks like. We have already seen that earlier, but again we have revisited that, and we have seen an interesting scenario where the flow regime was not known, but you have to calculate, let us say, the terminal velocity for a given or a known size of particle, or the particle size is known, you have to find out what its terminal velocity without knowing the flow region. I hope you should be able to calculate these things. We will see, we will solve some problems related to this particular thing in the next class. With that, thank you for your attention.